Hey there team, in this example I'm going to be showing you how to sketch sine and cosine graphs, but specifically I guess this example is more on sine. But let's have a look here. It says give a sequence of transformations which takes the graph of y equals sine of x, so that's your normal sine x graph, to the graph of what they've gotten here. So again, let's read this. Let's think about it logically first. So sine of x, y equals sine of x, what does that normally look like? Amplitude is 1, and clearly period is still going to be 2 pi. It doesn't get affected. So maximum 1, negative 1. Sine graphs look like this. So here we go. And we know their distance of 2 pi. So that means the middle is pi, and then clearly the quarter is pi on 2, and then the next quarter is 3 pi on 2. Okay? Great. So we've got our normal sine graph here. That's what our normal sine graph would look like. And in part A, we can see that now the amplitude, so the amplitude g of x, the amplitude is now 3, and that's being multiplied to sine of, notice that there's a dilation factor here as well. So we've got 3, which is the amplitude. I'm just going to fix here. So this is the amp. Amplitude is 3, so maximum now has changed to 3. And then notice that over here, this is going to squish the graph by a factor of half. Okay, so it compresses it. So essentially that's why your period ends up being the reciprocal of that dilation factor. So if it's 2, the reciprocal is half times the period, which normally is 2 pi. That's how long it is. That's why the rule is 2 pi on n, which in our case is 2 pi on 2, same thing. That's where it comes from. Okay, so the 2's cancel out and essentially you get pi. So what does this look like graphically before we even describe the transformation, okay? I want you to visualize every time you're working with these sine and cosine graphs to really visualize what's happening. So our graph now, our normal graph used to be from -1 to 1. Now it is from 3 to -3 because the amplitude, so it means it goes up and it goes down, comes back down. I'll just draw that again, just looked a bit terrible. There we go. That means the amplitude, so the distance from the center, top to bottom, is 3. Whoops, I should put 3 there, not negative. Okay, so amplitude can never be negative. So that's what it looks like. It looks like essentially if I were to draw it together, it means it's gone up by 3 and it's gone down, like that. Okay? But we also know the period has changed because it's no longer 2 pi. It doesn't take 2 pi distance to make one cycle. It actually now has changed by period to pi. So that means that the graph still goes up, comes back down, but it finishes at pi. Can you see how I've essentially compressed the graph? That's why when you write this out, this is what it looks like. There you go. That's what the graph technically looks like. But by comparison, this is what's happening. It goes up by 3, down to all the way through. Oh, sorry. Finishes at pi, actually. So it goes up, down, and finishes at pi. That's essentially what you've done. You stretched it vertically and you compressed it horizontally. Have a think of what I just said. Okay? All right, so now to describe the transformation. So state the amplitude, state the period, done, sweet. What's the sequence of transformations? Well, sequence, clearly, I've done A, and if you were to write it properly, this is what you're saying. You're saying a dilation of factor 3, okay, so you're stretching it vertically. So dilation of factor 3 from the x-axis. Why the x-axis? Because you're stretching it vertically, yeah? So you're moving it up, moving it down, so you're moving away from the x-axis. True? Okay, so that's why we say from the x-axis. And the other one is then a dilation factor of, so I realized I should have said dilation factor of, and in this case, remember, it's not 2, it's actually a compression. It's the reciprocal of 2. So hence it's a dilation factor of half, in our case, from the y-axis. Because it's a horizontal dilation or stretch or compression, you can think about it. If you're squishing it in, you see it's to do with the y-axis. Or if you stretch it out horizontally, you're moving away from the y-axis. Which is why the language, when you write it down, you say from the y-axis to let people know this is a horizontal dilation or horizontal transformation. Okay, so from the y-axis. And there you go. Those are my two, sequence of transformations for part A. And then you do the same thing for part B. We'll have a look at part B. We can do it a bit quicker now. So B, we've got g of x is 4 times sine of x on 2. Okay, so g of x is equal to 4 times sine of x on 2. Another way of looking at it is 4 times sine of half times x, if that helps you to visualize it. We again know this is the vertical dilation and this is the horizontal dilation, meaning horizontal stretch and vertical stretch. Okay, so we can see that again, this is the amplitude. So amplitude is clearly 4, so vertical stretch of 4. And then what I'm doing here now is again a dilation, which changes the period horizontally. So how long it takes to make one cycle. The period is 2 pi on half. Or another way of thinking about it is 2 times 2, which is 4 pi. Okay, so if I were to sketch this just so you can visualize again, your normal sine graph is like this. Okay, so 2 pi distance, 0, and maximum of 1 to negative 1, right? Now, you're doing a vertical stretch. So you stretch it up by 4, so amplitude is 4, so it goes up 4 times the amount, and goes 4 times down, and then it reaches 2 pi, if the period doesn't change. But there is a change in the period. The period is no longer 2 pi, it takes 4 pi to make one cycle. So now I need to stretch it out horizontally. So I've stretched it vertically, but I haven't stretched it horizontally. So the graph must be, if I needed to get to 4 pi, which is over here, to make one cycle, you would expect that I would reach halfway point by 2 pi, and then all the way down. That's what the graph has done. It's done a vertical stretch and a horizontal stretch out rather than a compression. So that's what my graph now looks like. I've stretched it vertically to a height of 4. I've stretched it horizontally by a factor of 2, essentially. Okay, so when you're describing this, I know it says half here, but remember it's the reciprocal. So when you write out your transformation, it's a dilation of factor 4 from the x-axis. Okay, so remember that's a vertical stretch, so away from the x-axis. And the second one is a dilation of factor, instead of half, it's not half, remember it's reciprocal, 2 from the y-axis. Okay, so that means I'm stretching it horizontally, and that's why my graph looks the way it does. And there you go, that's my transformation, but I wanted you to have a better idea. Every time you do these kind of things, you should try to visualize the problem. That's what methods is all about. Okay, so that's the first step. Hopefully you're starting to understand and read the transformations here. We haven't done any translations yet, it's all dilations.